Good morning, all of you. Today, we are going to discuss about the rectangular coordinate system. In a rectangular coordinate system, we set up three axes, namely x, y, and z, which are mutually perpendicular to one another. So this is x-axis, and this is y, and this is your z-axis. It is a customary thing to use a right-handed coordinate system, wherein rotation of x-axis into y-axis would cause a right-handed screw to progress along the direction. So in this diagram, if you look at this is x-axis, this is y, and this is going to be your z-axis. So if I turn the screw from x to y in the anti-clockwise direction, the screw progresses along the direction. That is what is meant by a right-handed coordinate system. And it is a customary thing to use a right-handed coordinate system. The reason for this is, afterwards when we discuss about the unit vectors, you're going to observe that ax cross ay is equal to az, ay cross az is equal to ax. So all these equations are valid only for right-handed coordinate system. And of course, without knowing that, we have been extensively using these equations um, in many in many times. In every coordinate system, you come across three mutually perpendicular surfaces. In the case of a rectangular coordinate system, all the three happen to be simple plane surfaces. X is equal to constant, y is equal to constant, and z is equal to constant. If you look at this one, x is equal to constant. So here, the green plane, basically it is a yz plane. Similarly, y is equal to constant, the orange one, and z is equal to constant, that is xy plane, that is the blue one. And one can see with the naked eye that all these three are mutually perpendicular to one another. And in fact, we are going to observe that intersection of all these three mutually perpendicular planes defines a point. Let us see how it happens. If I consider intersection of any of the two planes, it defines a line. For example, if you look at x is equal to x1 constant and y is equal to y1 constant planes, intersection of these two defines a line parallel to z-axis. For example, the back plane surface, let us say this is x is equal to 0. From there, at a distance of x1, if you imagine another yz plane, let me call this as x is equal to x1 constant. This is. Now similarly, the left hand surface, y is equal to 0. From there, at a distance of y1, from here, at a distance of y1, if you imagine another plane surface, that is y is equal to y1 constant plane. So intersection of these two, x is equal to x1 constant and y is equal to y1 constant, you can see that it defines a line parallel to z-axis, which is shown in the form of a red line. And if you observe this line is going to be present on x is equal to x1 as well as y is equal to y1 constant planes. That means at every point along this line, the value of x is fixed, x1. The value of y is also fixed, y is equal to y1. So when you go from one end to the other end of the line, only the z coordinate varies. Z varies right from minus infinity to plus infinity, depending upon the length of the line. Now here also in this diagram, intersection of x is equal to x1 and y is equal to y1 constant defines a line parallel to z-axis. Now, if we superimpose the third plane, z is equal to z1 constant, intersection of this line, which is parallel to z-axis, and z is equal to z1 constant, defines a point. That point has coordinates of x1, y1, and z1. So, one way of defining point P is it is a common point of intersection of the three mutually perpendicular planes of x is equal to x1 constant, y is equal to y1 constant, and z is equal to z1 constant. Now let us try to define point in a rectangular coordinate system. The simplest way of defining a point is, suppose there is a point with coordinates x1, y1, and z1. From that point, if I drop a perpendicular onto the bottom plane, z is equal to 0 plane, let us say the projected point is C. Now this is the projected point. X1 is the distance along x-axis, y1 is the distance along y-axis, and z1 is the distance along z-axis from this projected point C. So this is how actually a point can be defined in the simplest way. Basically x1, y1, z1 indicate distances along x-axis, y-axis, and z-axis respectively from the projected point C. But I prefer the earlier definition wherein actually a point can be defined as the common point of intersection of x is equal to x1, y is equal to y1, and z is equal to z1 constant planes. I prefer this definition with the simple reason that this definition can be extended for any coordinate system. For example, in cylindrical coordinate system, a point is represented by giving the coordinates rho, phi, and z. So, if there is a point P with coordinates rho 1, phi 1, and z1, it is a common point of intersection of rho is equal to rho 1 constant, phi is equal to phi 1 constant, and z is equal to z1 constant surfaces. Next, the unit vectors. So once again, the simplest way of defining a unit vector, for example, AX. AX is a unit vector whose magnitude is unity and direction is either along x-axis or parallel to x-axis. This is AX. Similarly, AY. This is AY. Magnitude is unity, direction is either along y-axis or parallel to y-axis. But once again, I want to slightly modify this definition and I want to define a unit vector AX as having a magnitude of unity whose direction is perpendicular to x is equal to constant plane. What is x is equal to constant plane? YZ plane. What is perpendicular to YZ plane? X direction. So this is how actually I would like to define the unit vector AX. Similarly, AY. Magnitude is unity whose direction is perpendicular to y is equal to constant plane. What is y is equal to constant plane? XZ plane. What is perpendicular to XZ plane? This y direction. Now once again, the reason for defining unit vector in this fashion is this definition is universal and it can be applied for any coordinate system. In the sense that suppose in spherical coordinates, the unit vectors are defined as AR, A theta, and A phi. AR is a unit vector having a magnitude of unity whose direction is perpendicular to r is equal to constant surface. Now, representation of a vector. Now, initially, let me consider a simple vector in the sense that it starts from the origin 0, 0, 0 and terminates at point P with coordinates x1, y1, z1. So the vector OP. From point P, when you drop a perpendicular onto the bottom plane, that is z is equal to 0 constant plane, let the projected point is C. And as we have already seen that this distance is x1. This is x1. So when this distance is x1, this also will be x1. This distance is also x1. So if I assign a direction of ax, so this vector becomes x1 ax. Similarly, this vector becomes y1 ay, and this is vector OC. So x1 ax plus y1 ay minus OC is equal to 0. x1 ax plus y1 ay minus OC is equal to 0. So OC is equal to x1 ax plus y1 ay. Now if you look at this triangle OP, and this is OC, and this is Z1 AZ. So OC plus Z1 AZ minus OP is equal to 0. So what is OP? OC plus Z1 AZ. OC is nothing but x1 AX plus y1 AY. So finally OP is equal to x1 AX plus y1 AY plus Z1 AZ. So if there is a simple vector that starts from the origin and terminates at point P, if you know the coordinates of the point x1, y1, z1, then you can write the vector OP as x1 ax plus y1 ay plus z1 az. Next, now is there any rule that every vector needs to start from the origin? No. You can have a vector PQ like this, which is not even passing through the origin. So how do you express this vector PQ? So what I'm going to do is vector OP is a simple vector that starts from the origin and terminates at point P. So vector OP is nothing but x1 ax plus y1 ay plus z1 az. Similarly, vector OQ, this is x2 ax plus y2 ay plus z2 az. Now if you look at this triangle OP plus PQ minus OQ is equal to 0. So PQ is equal to OQ minus OP. That is x2 minus x1 ax plus y2 minus y1 ay plus z2 minus z1 az. So if you know the coordinates of both P and Q, x1, y1, z1, x2, y2, z2 respectively, vector PQ is equal to x2 minus x1 ax, y2 minus y1 ay plus z2 minus z1 az. And if you want to find out the length PQ, the magnitude of PQ is nothing but root of x component x2 minus x1 whole square plus y component y2 minus y1 whole square plus z component is z2 minus z1 whole square. And if you want to find out a unit vector along the direction of PQ, APQ is equal to vector PQ divided by its magnitude. For example, say that the coordinates of point P are 2, 3, minus 1, and that of Q 4, 4, and 2. Then vector PQ is equal to 4 minus 2, that is 2ax, 4 minus 3, that is 1, and 2 minus of minus 1, so plus 3az. 2ax plus ay plus 3az. What is the length PQ, magnitude of PQ? Root of 2 square plus 1 square plus 3 square, root 14. And the unit vector APQ is equal to vector PQ divided by its magnitude. Now the expressions for differential length, differential area and differential volume. Differential means it is a fractional part. So in rectangular coordinates, what are the general expressions for the differential length, differential area and differential volume? So for this, assume that there is a point P with coordinates x1, y1 and z1. If I increase the coordinates by incremental values, differential values of dx, dy and dz respectively, then the new coordinates are going to be x1 plus dx, y1 plus dy, z1 plus dz. Now because there is a change in the coordinates, this defines another point Q. So point P has got coordinates x1, y1, z1 and Q has got coordinates of x1 plus dx, y1 plus dy, z1 plus dz. And if you recall how a point is defined, it is a common point of intersection of three mutually perpendicular plane surfaces. That means point P is a common point of intersection of the three mutually perpendicular surfaces of x is equal to x1, y is equal to y1 and z is equal to z1. So Q also, it is a common point of intersection of x1 plus dx is constant, y1 plus dy is equal to constant, z1 plus dz is equal to constant. So in defining each point P and point Q, we need three mutually perpendicular surfaces. In defining both P and Q, altogether 6 surfaces are involved. And these 6 surfaces represent a rectangular box like this. And here you can see that the front surface and the back surface, right hand surface, left hand surface, top and bottom surfaces. So these are the 6 surfaces. And these 6 surfaces are corresponding to x is equal to x1 constant, y is equal to y1 constant, z is equal to z1 constant, x is equal to x1 plus dx constant, y is equal to y1 plus dy constant, z is equal to z1 plus dz constant. Now let us try to match these 6 surfaces. Now if you look at this one rectangular box, this side is dx, this is dy and this is dz. Now how you're going to identify these 6 surfaces? In fact, there are 2 ways of identifying the surfaces. Now what exactly I mean is, suppose if you look at the front surface, does it represent y is equal to y1 constant or does it represent z is equal to z1 constant? So how you're going to map these 6 surfaces? Okay, so for that what we can do is, if you look at the front surface and the back surface, the front and back surfaces are lying in the YZ plane. That means x must be constant. So between these 2 surfaces, one should represent x is equal to x1 constant, the other should represent x is equal to x1 plus dx constant. Now because dx is positive, so the back surface represents x is equal to x1, the front surface represents x is equal to x1 plus dx. So that the distance between these 2 is equal to dx. Similarly, the left hand surface and the right hand surface, one can observe that both are lying in xz plane. That means y must be constant. So the left hand surface is y is equal to y1 constant, the right hand surface is y1 plus dy constant, so that the distance between these 2 is dy. Likewise, the top surface represents z1 plus dz, the bottom surface represents z is equal to z1 constant. So this is one way of identifying the surfaces. There is other way also. And if you look at this point P, through this point P, the back surface is passing, left hand surface is passing, and the bottom surface is passing. And if you look at the definition of point P, it is a common point of intersection of x is equal to x1 constant, y is equal to y1 constant, and z is equal to z1 constant. So if you look at the back surface, because it is lying in the yz plane, so it must be x is equal to x1 constant because it is passing through point P and the x coordinate of point P is x1. Similarly, the left hand surface, which is lying in the xz plane, y must be constant. So what is the y coordinate of point P? It is y1. Similarly, the bottom surface is z is equal to z1 constant. Similarly, if you look at point Q, the front surface is passing, which is lying in the yz plane. So what is the x coordinate? That means x must be constant. What is the x coordinate of Q? x1 plus dx is constant. Similarly, the right hand surface, which lies in the xz plane, y must be constant. What is y coordinate of point Q? y1 plus dy. Similarly, the top surface which lies in xy plane, z must be constant, so it has to be z1 plus dz. So this is another way of identifying the surfaces. Now, just now we have seen that if you know the coordinates of point P, let us say x1, y1, z1, and point Q, x2, y2, z2, we know how to write the vector PQ. X2 minus x1 ax plus y2 minus y1 ay plus z2 minus z1 az. Now, because we know the coordinates of point P, x1, y1, z1, that of Q, x1 plus dx plus y1 plus dy and z1 plus dz. So when I apply this equation, dl becomes, PQ becomes dx ax plus dy ay plus dz az. So that is the general expression for dl. Now the differential area. Sometimes in electromagnetic theory, we need to define surface as a vector quantity. Remember that whenever we want to define area as a vector, the only direction that we need to assign is the outward normal. For example, if you look at the front surface, this dimension is dy, this dimension is dz, and what is the direction of this surface perpendicular to dy and dz? That means it has to be x direction. Similarly, the right hand surface, dx into dz into ay. Top surface, dx into dy into az. So this is the general expression for ds. dx dy az plus dz dx ay dy dz ax. And finally, the volume is volume of the rectangular box, dx into dy into dz. And one of the most important things that you need to observe, if you look at these expressions, for obtaining dl, it is enough to vary one coordinate only, either x or y or z. But for obtaining area, we need to vary two coordinates at a time, dx into dy, keeping z constant, dz into dx, keeping y constant, dy into dz, keeping x constant. So we need to necessarily vary two coordinates, keeping the third one constant for obtaining area. And of course, for obtaining volume, all the three have to be varied. And this is applicable for every coordinate system. Something like you're dealing with a spherical surface of an area of 4 pi r square. The immediate point that should come to your mind is we're defining an area of 4 pi r square. So naturally, we need to vary two coordinates simultaneously, okay, keeping the third one constant. So now, how to make use of these equations? That is more important. For example, I have a rectangular area which lies in z is equal to 0 plane The x coordinate is varying from 1 to 5. That means this dimension is 4. And the y coordinate is varying from 1 to 3. So this dimension is 2. So what is the area? 4 into 2, that is 8 square meters. Now let us try to obtain this area by making use of the equations. The first point is, because we are dealing with area, I need to make use of this equation. ds is equal to dx dy dz dx plus dy dz ax. And there are three terms here. How to pick up the appropriate term? So further, there are two ways. One way is both x and y are varied to get this area. What is constant? Z is constant. As we already discussed, whenever we obtain an area, we need to vary two coordinates simultaneously and keeping the third one constant. So here Z is constant. Once Z is constant, dz is 0. That if I substitute this term dz into dx, this term would be 0. Similarly, dy into dz, this term also would be 0. You are left with ds is equal to dx dy into az. Okay, ds is equal to dx dy az. Magnitude of ds is equal to dx into dy. So that is one way of picking up the appropriate term. There is another way also, looking at the direction. What is area? This is the area under question. Now, if at all I want to represent this area as a vector, what is the direction I need to assign? It is the outward normal. What is this direction? Z direction. So, out of these three terms, pick up the term which has got a direction of az. So, that is dx dy az. So, this is another way of getting on to the right or appropriate term. So ds is equal to dx into dy. What is the total area? S is equal to double integral dx dy. X varies from 1 to 5 and y varies from 1 to 3. So ultimately you get this as 8 square meters. And then coming to about the unit vectors, in rectangular coordinates we define the unit vectors as ax, ay and az. So already we have defined a unit vector ax is having a magnitude of unity whose direction is perpendicular to x is equal to constant plane. X is equal to constant plane means yz plane. What is perpendicular to yz plane? It is x direction. So this is how we define the unit vector. Okay. And when you apply the dot product and cross product, suppose there are two vectors a and b. What is the dot product a dot b? Magnitude of a into magnitude of b into cos theta. That is a scalar quantity. Similarly, vector, the cross product a cross b is equal to magnitude is equal to ab sin theta, and the direction is perpendicular to the plane containing a and b. Okay. If I apply these equations, you get this as ax dot ax, ay dot ay, az dot az is equal to 1, ax dot ay, a dot az dot ax is equal to 0. Similarly, the cross product ax cross ax is equal to 0, ay cross ay, az cross az is equal to 0, ax cross ay is equal to az, ay cross az is equal to ax, az cross ax is equal to ay. Now, especially when you apply this cross product, there is a very possibility that you may get confused. To avoid that, I'll tell you a simple technique. X, Y, Z, X, Y. In the forward direction, ax cross ay is equal to az, ay cross az is equal to ax, az cross ax is equal to ay. You get only the positive values. In the reverse direction, ay cross ax is equal to minus az, ax cross az is equal to minus ay, and az cross ay is equal to minus ax. So this is how actually you can remember these equations. Okay, this is all about the rectangular coordinate system. In the next class, we are going to discuss about the cylindrical coordinate system.